Okay, let's take a look at the take-home test 29 through 35. 29, here's the function e to the 3x over sine x squared, and they just want to know the derivative. So, just looks like the quotient rule again, so we have f and g, and just to help you out, sometimes it's easier to write the derivatives up here. E to the 3x times 3 using the chain rule, and g prime. Well, here this is a chain rule, this bottom part. So the derivative of sine is cosine, and the angle is x squared, and then the derivative times the derivative of the angle, which is 2x. So I'll let you put that together, and you may have to simplify a little bit, maybe combine like terms, and see what you get. Okay, let's take a look at number 30. Number 30, they give you that the function is e to the 2x, and they tell you that the derivative is equal to 10 at some x value, right? So we have to figure out what the equation of the tangent line is. So eventually we're going to do what? Y minus f of some value a, which we don't know yet, equal to the derivative at that same a that we're not sure about. Well, actually we do know this value, right? The derivative at a is equal to 10, so we got to find this x value, or this a, times x minus whatever that a is. So the only thing that we know right now for certain is that that's going to equal to 10. So let's take the derivative first to see what we get. The derivative is equal to e to the 2x times 2. Chain rule of the exponent. So when does that equal to 10? That's what we need to find out so we can solve for x. So when does it equal to 10? Well, we could divide by 2, and we can figure out when e to the 2x is equal to 5. And how do we get rid of the variable when it's in the exponent? Well, you take the natural log of this base, or the logarithm of this base, which is the natural log. So the ln of e to the 2x is equal to what? The ln of 5. Well, the natural log and e are going to cancel out, so you get 2x is equal to the natural log of 5. So x is equal to natural log of 5 over 2. Okay, I'm going to erase this except for the answer part, so hope everyone has this part. If not, you can just pause the video. So let's write down, well, let's look at the answer choices. The answer choices all have, they don't have anything about the natural log of 5 over 2. So let's go to our calculator and calculate this x value. Let's see, the natural log of 5, close the parentheses and divide that by 2, and we get 0.805. Okay, so let's just jot that down over here, and you can see that's appearing in the answer choices, 0.805. And now we have to go back to the original function and find out what is the function value at 0.805. So let's see what we can do with that. So we have second e raised to the what? 2 times the answer. And lo and behold, it's equal to 5. Well, we kind of expected that anyway. So the function value there is equal to 5. So we have y minus 5 is equal to 10 times x minus 0.805. Okay. So the answers are all solved for y. So we'll just move everything over, distribute that, and you get 10x. Distribute 10 times that, and you get 8.05. And you're going to add 5 to it. So if you add 5 to it, what do you get? You get 5, or excuse me, this is a negative 0.805, right? So we have to add 5, we have to subtract 0.805. So if you do that, you should be able to clean this up and get 10x minus, what is it, 3.05? Whoops. I didn't distribute this over here, did I? It's 5 positive and then minus 8.05. There we go. So go ahead and clean that up and you should find your answer there. Now since we've already gone this far, it's just going to be minus 305, right? Alright. Let's move on to number 31. 31, the answer choices all are asking about the function. Is it greater at 2? Is it greater at 0? 4, 6. So this is kind of a problem that's asking you if you can identify what they've given you. Well, they've given us that this is the graph of the derivative, right? So what does a graph of the derivative tell us? It tells us where it's increasing, where it's decreasing, where it's equal to 0, and what about the graph's second derivative? Second derivative tells us whether it's concave up or concave down, which might help us. So let's just do a little chart underneath here. So this is the derivative, not the second derivative, the first derivative. From 0 to 2, this thing is what? Increasing. And I just lied to you. It looks like it goes from 0 to about 1, right? So from 0 to, we're going to have to estimate somewhere around 1, it's decreasing because it's negative. And then from, say, 1 all the way to 4, since it's above the x-axis, it's increasing. And then from 4 to 6, it is negative, right? And what happens right here, the derivative changes from positive to negative. So increasing, it's 0 there, right? Here it's decreasing and then it starts increasing. Increasing all the way here, decreasing in this interval. So let's see. What about the concavity of this thing? In case we need it. It's nice to have it. So the slope of this first derivative gives us the second derivative, right? So from 0 all the way up to 2, so right about there, from 0 to 2, this thing is positive, so it's concave up. Concave up. And then from sometime around 3, it's 0 in here, right? And over here its slope is negative, so it's always concave down. So hopefully that'll help you get set up. And it looks like this area in here, let me just focus in on this right here. Let's see if we can just maybe help you out a little bit. The function starts off at 0 and it's decreasing, so when you get to 0.5, it's smaller than it was at 0. And it starts increasing somewhere around 1, and it keeps getting bigger and bigger and bigger until it does what? Hits 4. So we know that f at 4 is going to be the greatest. Alright? Because after that it's decreasing all the way. So a good place to start is eliminating answers. So you know f4 is bigger, right? And so you just have to start comparing answers, and it's going to be a little bit deceiving, but it reaches its greatest and then it decreases. But look at this rate of decrease right here. This slope, which I just made green, is less steep than this slope over here. So that's going to be a hint as to what the next value is. Alright, I'll let you work on that a little bit. And let's take a look at 32. 32 gives us these 3 statements, and we have to tell whether it's true or false. First thing I notice is that this is the limit definition for the derivative, right? You got your h going to 0, and they're telling us that the derivative is equal to 3 at the function value 5. So that doesn't mean that the function itself is equal to 3, just the derivative. So the derivative at 5 is equal to 3. That's true. Now the question you need to think about is, if you can take the derivative, is the function continuous? And is it differentiable? Well, you know it's differentiable because you have a derivative. And in order to take the derivative, one of the conditions is that it has to be continuous at that point. So that's 32 for you. Okay. And let's take a look at 33. 33 has, they've given you the derivative, right? And they want to know, where does it have a local maximum? Well, in order for a derivative to have the local maximum, it would be what? So at this point right here we have a local max. Call that point A. Well, let's take a look at the derivative. The derivative is positive to the left, and then it reaches 0 at A, and then it becomes negative on the other side, right? So we have to look for when the derivative is going from positive to negative and passing through 0. So let's just take a look at this graph. I've already put it in the calculator, I think. And there it is. So I adjusted my window earlier and made the Y max bigger so I could see everything happening. So here, remember what we're looking for. We're looking for when it goes from positive to negative. Here it's going from negative to positive, so this points out. We're still positive here. You can see my pointer. We're still positive, and then we go to 0, and then we hit negative. So we need to find this point right here. So I'm just going to cheat and just use the trace button, and I'm just going to type out some of the answers. I know that this looks like it's a little bit. Let me zoom in on this since you can see it now. Zoom in. So we're looking for this point right here, and I can move my mouse around and see that it's around 0.5 something. And there's only one choice that looks good, 0.511. Let's try it. Trace 0.511. If that's equal to 0 there, we're good to go. And it's close enough, 0.00216. So, alright, we'll pause here for a second. When you want to talk to the camera, Lyle? You want to come talk to the camera?
Yeah.
Say something. I'm going to spell something. You tell me what I'm spelling.
What is it?
What is that?
What's that name?
I don't know. Whose name is that? Is that you?
No. You missed the name.
I missed it. What is it supposed to say?
L-Y-L-E.
Like this? Is that better?
Yeah.
Okay, say bye-bye.
Papa.
Okay. Alright, let's take a look at 34. 34 is a word problem that you're probably not going to like a whole lot, but it's not too bad. It tells us that car A is going south at 40 miles an hour. So we're going to think of that as maybe in the y direction, right? So this would be dy dt. And it looks like another car is traveling west at 30 miles an hour. And both began traveling, looks like 100 miles outside of some town at the same time. So the other one starts off over here, let's say, and it's traveling this direction. And it wants to know, it's going at 30 miles an hour. So we'll call that in the x direction, so we'll call that dx dt. And when they first started, here and here, they were 100 miles apart. So both of these are at 100, right? 100 miles away from this town right here. Right, where the two arrows came together. Let me make it red, make it real clear. So here's the town. Okay, it says they want to know what is the distance between them decreasing after 90 minutes. Alright, so they want to know, let's call this distance z, the hypotenuse, okay? And they want to know how is dz dt decreasing? Okay, well, after 90 minutes, what's the distance? What's the x distance? So after 90 minutes, it's traveled an hour and a half. So this thing has gone, what, 60 miles? And the blue car here is going, what, 45 miles. Alright. So the blue car's gone 45 miles here from starting point to here. So that's 45. What's left? Looks like 55 miles are left for him to travel. And this green car has gone 60 miles. And so we have 40 miles left to travel. So they're 40 miles away from the town, and the blue car is 55 miles away. So let me just redraw that. So there's what's left. 40, and the blue car has a little more, 55. And we use red, so we want to know what this is. Alright. So, still traveling at a constant rate. Well, let's just go back to the original equation. Pythagorean's theory, right? X squared plus y squared is going to equal that z squared. So taking the derivative, you get 2x dx dt plus 2y dy dt equals 2 times z dz dt. And of course you could divide everything by 2 and get rid of the 2's. And you know what x is equal to? X is equal to this, the blue one is x, right? So that's, let's see if we can keep the color straight. We have 55, and dx dt is equal to what, 30? Plus y, the green car, is 40 miles away, right? And he's traveling at 40 miles an hour, dy dt. And we have to figure out what z is equal to so we can solve for dz dt. So 40, so we have what? 40 plus 55 squared, square root of that, using Pythagoras theory there. So we have 40 squared plus 55 squared, and we're going to take the square root of that. And what do we get? 68. So we just crank these out on the calculator and divide by 68. And that should tell us dz dt. So let's see if we can scoot this over a little bit. And if you crank out that calculation, plus 40 times 40, and divide that by 68, and it looks like we got an answer. Okay. Alright, let's see if we can look at 35 real quick. X squared minus 1, the absolute value, over x minus 1. And it's another one of those conditional problems where true, false. Well, first of all, x cannot equal 1 in this equation because that's the denominator. So let's keep that in mind. And let's just put it in the calculator and graph it up and see what we get. So we have the absolute value, math, over the number, right? And we have x squared minus 1. And we're going to divide that by x minus 1. Make sure you put the parentheses. When in doubt, wrap it up. And let's zoom 6 just to start. Yep. Wow, that looks crazy, huh? Make sure we put that in there, right? Absolute value of x squared minus 1 divided by x minus 1. Looks good? Okay. So let's take a picture of that, and is it continuous at -1? Well, no reason to second guess if we have the calculator up here. We can put our cursor right at -1, and it certainly looks like it's continuous, right? Is it differentiable there at -1? No. So at -1 it's continuous, so number 1 is true. Number 2 is asking us about is it differentiable at x equals 1? So at x equals 1, let's just trace it, but it looks like it's at that sharp corner there. See the sharp corner right there? So at x equals 1, it is not differentiable. So number 2 is false. And does it have a local maximum at x equals -1? At x equals -1. Well, let's zoom in on that. Sure looks like it does, doesn't it? Let me get over here just a little bit down. Zoom in on that -1 a little bit. And trace it so we can make sure we're at the right spot. At -1, certainly looks like it has a local maximum, so 3 is true. So just go through your conditional statements and figure it out. Alright, let's take a look at number 36. (36) tells us that y is equal to 3x minus 7, and x has to be greater than or equal to 0. And what is the minimum? The minimum product of x squared times y. So we're trying to maximize this product. So we have to take the derivative of this, but we notice that we have two variables. So we use our equation y equals 3x minus 7, and that's our product, right? Call it p. So if we take the derivative of this p function, we have 3x cubed minus 7x squared. So the derivative of this would be what? 9x squared minus the 14x. And let's take a look. Find the critical points, right? So what's common is they both have an x in it, so we have 9x minus 14. So critical points are when x is equal to 0. Is that in our statement? Yep. And the other one was when x is 14 over 9. So 0 and 14 over 9. Well, we're restricted to this over here, right? We're looking for local minimum. So remember, local minimums look like this. So that's where the derivative is negative, and then it either hits a 0 or undefined spot, right? So we decrease to increase. So let's see what happens here. So pick out a number between 0 and less than 1. No, this is greater than 1, right? So you could use 1. This is easy enough not to use a calculator on this one. So at x equals 1, somewhere in here, right? We have positive 1 times 9 minus 14, so it's negative. So looks like it's starting to set up okay here. And what happens over here? Pick a number big, like say 5. 5, and 9 times 5 is 45. Subtract 14, it's still positive, so we have positive. So it looks like it very well could be that. So our minimum value is 14 over 9. So what do? This is x, right? So let's go look at what is the product of x squared times y. And so we just put that in our calculator. X squared using our 14 over 9. Okay. So if we do this properly, use our parentheses and all that, we have 14 over 9 squared. Over 9, square that, and then give us another parentheses, come on. 3 times another parentheses, 14 over 9. Close that parentheses, subtract 7, and close it. And we get a negative 5 point something, okay. Alright. Let's take a look at 37. Since we're on the calculator already, let's just put these two functions in the calculator. 37 has sine of x make sure I'm still in radians here. Should be. Yep. Where were we? There we go. Sine of x and 1/4 x minus 1, so 0.25x minus 1. Alright. Now zoom trig on it. Alright, it says bounded by this sine of x and 1/4 x minus 1, and not the x-axis this time, but the y-axis. So, looks like all this area right here. I don't know if I can draw this or not. Let's see, what can we do? Let's see if I can take a picture of this real quick. Okay. Alright. Let's move this out of the way. Move this over here. Okay. Now, the y-axis in this area would be this. So we have to figure out where this intersection is. And looks like we're going to go from 0 to whatever that intersection is. We'll call that point A. And the top curve minus the bottom curve, right? So it looks like it's going to be sine of x minus the second function, 0.25x minus 1. And remember, we put this in y1 and we put this one in y2. So this will be good practice for the calculator. We have, first we got to find that intersection, right? So we'll go second, calculate. And we're looking for number 5, the intersect. And enter, and enter, and enter. 0.331. I'm going to store that. Store that in A to make my life easy. Alright, alpha A. And then I'm going to do math. And numerical integrator number 9. And we said y1 minus y2. Minus, do it again. Variables function, this time number 2. And let's see, if we remember the syntax, it's the variable's x, the lower limit is 0, and the upper limit we stored it in A, so recall it by doing alpha A. Come on, there you go. Close that parentheses off, hit that enter button. There you go. 3.92. Okay, just a word about number 38. This is no longer tested on the A/B test. They don't require you to do the shell method. So let's skip that one. The answer is E. But if you want to try it, the integral is 2 pi 0 to wherever it intersects, right? And then it's going to be always this x is in here. That's the radius, if you will. And it's sine of x minus 0.5x. And we're rotating it this time. We're going about the y-axis. So this is just a way to find the, without having to resolve for y. So we'll skip that one. Alright. And let's look at 39. Hopefully we're coming to a conclusion here soon. The video's running kind of long. So I think I'll stop it here. And we'll pick up with the rest in a minute.